Okay, so for those on the video, I just remembered I hadn't turned down the recording. So an acid is a compound that dissociates an H plus ion. If it's got an H there, it has the potential to be an acid, but only if it comes off, dissociates. A base is the same thing, only a different. So if it has an OH, a lot of things, particularly biochemically, have OHs on it. But very few of them come off. Okay, how can water be both an acid and a base? Well, if you look at the formula for waters, as you all know, is H2O. If you look at it like this, it's got an H and an OH, and it disassociates. That. So this is why it meets both definitions. It can disassociate an H plus, disassociate an OH minus.
Okay, prefer this, right, H plus plus OH.
Instead of writing my little description.
Right.
Well, you need more than that, though. I know where you were going with that, but just mention that both an H and an OH disassociate. Hence, it fulfills the definition of both an acid and a base. Okay, initials on the back of the, and don't forget your take-home problem. Make sure you bring that in, staple it to the back of your test, on the back of your take-home test question, put your initials. And you get a quick 5 points for that. All right, correct the following electronic configuration. Well, let's see here. We go 1s2 looks good, 2s2, 2p6, 3s2. This is wrong. And this should be 3p6, 4s2. Now you can add to that, but whatever you add, you end up needing it to be correct. Okay? For example, I could go and that would be fine too. Just basically fill in the gaps it's missing. All right, what's the electronic configuration for iron? Now I included a periodic table for you. So you need to figure out where iron is located on the periodic table. Okay, so here's iron right here. And it is 1, 2, 3, 4, 5, 6n. The 3d electrons. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay. Now, if we did the periodic table journey, we would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6n. Either way works. Now let's say I wanted an orbital diagram as well. That would be the orbital diagram for. Okay, so those make sense? Oh, and I answer the next question. That would be the, okay, what is a valid Ba ion and write its orbital configuration? Well, let's start with just the Ba neutral atom first. Okay, so what does that look like? Well, barium is right here. So that's barium. So that looks like it's so that goes all the way down to the 6th shell now. But we're not doing F's, we're only doing D's. So that would be okay, so that's gonna be 1s2, 2s2, 2p6, 3s2, 3p6. Four S2, 3D10, 4p6, 5s2, 4d10, 5p6, 6s2. That's for barium metal. Okay, so let's do the orbital version of that. And let's only look at the this part, starting at the 5th shell. So this is what it's going to look like, because everything else is all full. So none of those are going to come, those electrons are not going to come off or be captured. Okay, so we're going to look at 5s2, four D10. That's 5 of these now. And then we need 5p6. And then we have 6s2. And we have 5Ds, but not, they're empty orbitals. Okay, so that's barium. What would be a good remember the 4 stability guidelines I gave you. A full shell is the most stable. A full subshell is stable, but not as a full shell, and then a half full subshell. Those are the three main stable configurations. So you want to move electrons in or out to fulfill those, to stabilize the atom. Now, right now, we've got, we do have a full subshell. So barium is not too bad off. But if we're going to do an ion, what would it be? Someone said two something. Marie, was that you?
No.
I can't force you to answer it. What would be a good ion?
BA plus 2.
Let's look at Ba plus 2. If we took 2 electrons away, we would end up with a full shell. So if these 2 left, so we would have so now we have a full shell. So barium plus 2 is very stable. So if you were to go out into nature and try to find barium metal, you would not be able to find it. You find lots of barium oxide. Because the Ba plus 2 wants to hook up with another ion. And most of the time it's oxides. So that would be also called barium ore. Okay, so does that make sense? Plus 2 ions are very common. Because you have that S2 that can leave. So frequently when you see common ions, you'll see a plus 2 in there, assuming it's a metal. Okay, we okay with, yeah.
Isn't it just based on which column the?
Sure, you can-
So we can just reference that. Plus 1, plus 2, plus 3, plus or minus 4. So we can just reference things. That. Yeah, it's very on tape, we can just reference what column it's in, not all the words. Yeah. Okay.
And you can also mention everything in column 2. Column 1 is got only 1/5 electron. So that's why they call it plus 1. All right, everyone, yeah.
I got 3, not 3 6. How did you get 6?
Well, it started with 6, so I just kept 6.
Well, the question after your initial the back of the tape.
I'm still not. So what question are we referring to? Let's go.
Initial the back of the tape home problem.
Okay, all right, let me see here.
Question. At the acronym.
Yeah,
Then this is one of the words.
so what was your question?
Yeah.
Which one? What column? Top. Because I'll try to get which.
So how did you go, what did you have down for an answer?
2s2, 2p6, 3s2, 3p6, 4s2, 3d5.
And why not six?
How much?
Did you count total electrons? Okay, so that's how you ended up with the five. Right? Okay. Neither one's correct. I just said correct it. So you're not limited to sticking with the number of electrons. It works, but so there's bottom line is there are multiple answers to this that are correct. And so your answer would be fine.
Wouldn't you,
Huh?
Professor,
Yeah.
wouldn't you fully fill these operations on?
You gotta fill.
So it'd be 3p6. Okay.
Yeah, just, she counted the big. But when you're writing out, make sure that you've got all that earlier stuff at the phone.
Yeah. That's what she just-
Okay, okay, on this one's a gas problem, and the R value I gave you was different than the R value we used in lecture. So, use the one that's on the tests, even though it's not the same one we used in lecture. Okay, so, we're using PB. Yeah,
Page. Next step. Yeah, we're still on it. We're still on the test, not the take home test.
Oh, that's not.
I mean, the second page. Since before the 6 days, there's a balance.
What is the orbital configuration from here?
okay. Okay, so you gotta locate where chromium is located in the periodic table. So how far in is it into the Ds? How far in the Ds? 4N, okay. So let's do this thing. You say it was 4N?
I think. Three,
Yeah.
4, yeah.
Okay. Okay, so that would be. There are two right answers for this one. And some of you figured it out. If you look up the chromium electronic configuration, you won't get the 4s2. You're going to get a 4s1, 3d5. And what that is, it's called bond hybridization. We're taking one of the s electrons, moves it over to here. So we're destabilizing 1, stabilizing 5. So the 5 wins over the 1. But either one of those would work fine. Because I didn't talk about bond hybridization here. Copper does the same thing. So everyone in that group does the same bond hybridization. Okay. When I loaded this, it loaded three of the tests rather than just one. Okay, all right, we're gonna do. Okay, so we're gonna use PV is equal to nRT. And R is going to be equal to. That's what, that's what I did at the bottom of the test. So we're gonna use that value. Okay, temperature is. This is not a gas problem. What am I doing? The other one was a gas problem. Yes, I agree. Okay. So we've got two containers. And the idea here is to find the final concentration after we. Dump one into the other. Okay, so this is going to be 234 liters. Concentration is 465 moles per liter. This one is 143 liters and 234. Now, if you remember, concentration times volume equals moles. So the idea in the final concentration, we need to know the moles, we need to know the volume. So moles are going to multiply these two together plus these two together, and that'll give us total moles. So 465. Okay, now we have moles per liter. Okay, so all these combination deals, you need to look at moles when combined, volume when combined. So does this make sense? It will by tomorrow, right? Okay, right? Separate hydrogen ion and chloride ion concentrations for HCl. Now remember, hydrochloric acid is hydrogen chloride gas in water. That means it's H plus plus Cl minus. Balance it. 1, 1, 1. So if we know the concentration of this, we know the concentration of this and that, because these two are equal, because the coefficients are 1 to 1. Okay, so let's look at the concentration of HCl. And that automatically equals H and automatically equals chloride. Okay, so we've got and is it, who's already done this? What's the molar mass for HCl?
36. 46.
Say again? 3346?
It's 36, 46.
Like that. Okay, so that'll give us a concentration of HCl. And that's also the concentration of H and the concentration of chloride. Because it's 1 to 1 to 1. And remember, strong acid totally disassociates. There's none of the original left over. Trick question. What is the concentration of HCl? What's the concentration of HCl? Not H, not Cl, but HCl.
Was it the?
Hmm?
Yeah, that's what.
Now think, wait a minute, before you answer, think about the definition of a strong acid. Okay, that means 100% disassociates. So how much of the original is left? None. And that's true for all the strong acids, there's 7 of them. And we work with mostly HCl because it's the simplest one. Okay, so everything is converted, nothing's left over. Okay, does that make sense? Okay, what's the volume in liters of a gas balloon? The gas pressure is 0.3 atmospheres and 24.5 centigrade or Celsius. Let's convert the Celsius to Kelvin.
Professor, Professor,
So which is smaller?
Professor,
Celsius
please, I have
or
a
Kelvin?
question.
Celsius is smaller, that means we need to add to get up to Kelvin. If we started with Kelvin going to Celsius, Celsius is smaller, so that means we got to subtract out the 273. And what is that going to be? It's going to be
278.
And then
279.5. Okay, and R is going to be okay, so we just plug it in. Now we want to know volume. We solve for V. Okay, so Misty, since N is not given, what should it be? She emailed me this question, that's why I'm asked. 1. So if the if the moles are not, I didn't mean to,
Oh, it's the same.
so if the moles aren't given, assume it's 1 mole. So that's gonna be 1 times. Now, do I need to multiply by 1 on my calculator? No. You can if you want, but you don't have to. 1 is always optional. You multiply by 1 or divide by 1, just ignore it. Now, N is if you add gas atoms, or if you take gas atoms away, that's where N comes into play. But if it's just a balloon where gas doesn't enter or leave, it remains the same. At 1. Okay, all right, so we've got a balloon now again, starting at certain temperature, rising, pressure decreased at the new volume. So remember that was PV. And there's an N in here as well. Now, why isn't there an R there? The 805 number? Well, assuming I multiplied correctly. Yeah, I just multiplied,
Everything on the top.
Yeah, same, I got 80.5.
really? What R value did you use? The one, the 812? I get the same answer. Only, oh, it's not times, it's times 1.
Yeah, if it was 3 times, it would be 8.
Right. Yeah, 80.5.
But can we just do 80.5 as well?
Yeah. Remember, is 80.5 awkward for you? No, leave it then. If it's not, if you feel it's awkward, then convert to scientific notation. I'm just reading what my calculator said. I don't understand how I missed that. Oh, I didn't put a decimal point in. I put in 812. Okay, so we want to know the final volume. Okay, so if we put all these numbers in, this is what we want to find right here. So we have an initial pressure of 122. Initial volume of okay, and then initial temperature of if we solve for V sub F, we're gonna get Pi Vi Ti times the inverse of this, which is T sub F over P sub F. So this is the first term here. Now we need the temperature, just 29.5. Okay, so basically, I went from here to here by solving for V sub F, the final volume, which means I multiply everything by the inverse of what it's being multiplied by. The inverse of that is T over P final. That's how I isolated the V sub F. Okay, so let's. By the way, if any of you have an 84 or an 89 or an 83, and it goes screensaver and comes back on, don't start typing right away. It has to just give it a couple extra seconds, because that's what happened above. It cut off the decimal point because I typed it too fast. Every other calculator, it's immediate, except 84, 83, and 89. Okay, so let's see here. So the new volume is going to be okay, so this is the guy here where everything is centered on. Did you all get 101?
I got 1.2. But I'm sure
It's three sig figs though. Oh, it's 2 sig figs on the 0.54. Yes. I'm so used to 3 sig figs because of the slide rule days. Okay. All right. Nuclear chemistry. All right. So balancing these equations. We've got the top numbers have to be equal to the bottom numbers. And we're always gonna have a little bit of. Define what's missing here. Okay, so let's do the bottom one. That looks the easiest. Okay, so 22 plus what is equal to 22? 0. Okay, so the bottom number in sodium is missing. What should it be? Huh? 11, yes. So 11 plus what equals 10? -1. So what is 0 over -1? What particle is that? Huh? Electron, right. Okay. Think of this as an equal sign. So let's look at beryllium here. What is the bottom number for beryllium? Okay, so 4 times or 4 plus 0 is what? Oh, it's 3 O's, don't forget. Three zeros. So 4 plus 3 zeros is what? 4. And over here we have 2 plus what is 4? 2. Okay, what about the top here? 9 plus 3 is what? 12. 4 plus what is 12? 8. Okay, so we have a conundrum now. Do we have a particle of 8 and 2? No, but we've got a one of 4 and 1. So instead of 8 over 2, we can go 2 4 over 1s, which is a alpha particle. So that's a
Is gonna be another.
actually, we're gonna change this. Okay, the 12 is on which side? Let's just do, let's do both sides again. Okay, on the left side, we have 9 and 3 1s. That's how I got 12 on the left. Okay, on the right, I've got 4 plus what is 12? 8. Well, we don't have a particle that's 8 over 2. We do have one that's 4 over 1, which is a multiple of 8 over 2. That's why we can have 2 of them. So 2 times 4 is 8. 2 times 1 is 2. Okay, that makes sense? Huh?
I'll be a 9.
A 9?
You look at the end, there's a 3 in front of it, and then the 1. So those words.
So you have 3 1s plus the 9. So you're talking about on the left. Yeah. Okay, let's go up here. Okay, 218. 1 plus what is 218? $217. Actually, it's 216. Why is it 216? There are 2 neutrons there. So 2 times 1 is 2 plus 216 is 218. Okay, and what's the bottom number for polonium? What is it? 34?
80.
84. Okay, so 0 plus what is 84? 84. So what's the element? Yeah, it's the same thing. Why is it the same thing? Because the bottom number determines the element. That's how many protons are there. So we did not change the number of protons. That means the element stayed the same. So we created an isotope. So the first one lost 2 neutrons. But neutrons have no protons. Okay, and then the last one we have 253 and 8. 261. $99 plus 4 would be 103. Okay, so 2 plus what is equal to 261? So we have 2 times 1 is 2, plus 259 is 261. Okay, and what about the bottom? 2 times 0 is 0. 0 plus what is 103? And what element is 103? LR. LR was named after the Lawrence Livermore Labs. Okay. So does that make sense? Make the top numbers equal, bottom numbers equal. Which one? The beryllium one.
Yeah, no. Like how you got the names that 2, 4 over 1.
Is that the second one?
The third one.
Third one, okay. Okay, beryllium 9 means it's got 9 on the top. And we have 3 neutrons over here. Each one has got a 1 on the top. So we have 9 plus 3 times 1. That's how I got the 12. Is that your question?
I got that part. I'm talking about the end.
The 2,
The
4,
2, 4 over 1.
It would be 8 also too.
We just ate
I
it.
got 8 over 2.
Yeah, if you get 2.
You just
Oh.
changed it around because there's no element with either with this. That's it. So he put it like 2, 4 over 1. So if you times the 2 to the 4, it'll be 8, and then 2 times to the denominator 1.
So it doesn't need an element.
Well, it's an alpha particle. So it's not an element. I mean, it's kind of an element. Is that okay now?
Yeah, it makes sense. I see the 4 over. That makes sense.
Yeah, that was kind of a tricky one. All the rest are slam dunk. Now, if you put out 8 over 2 and left it like that, I would ding you 1 point. Because you did the right thing. Just that doesn't exist. That would be a helium atom with 6 neutrons in it, which. All right. Okay, last one's on half-life. So you can do this a couple different ways, like always. Let's do the graphic one first. Okay, so what's the initial mass? $534 grams. Okay, and what's the half-life? So after 1 half-life, 34 minutes, it's going to be what? Half of 234 is what? What is that? 257? Okay, we're not at 102 minutes yet, so we have to go through another half-life. Okay, half of 267 is. Okay. We need to do another one to get to 102. And then half of that is what? 75? So that's the final mass. 34 plus 34 plus 34 is 102. Okay, is everyone okay with the graphic method? And the other way to do it. So we've got the initial mass. Final mass, which we don't know what that is. The initial mass is 534. And what else? The elapsed time is 102 minutes. Half-life is 34 minutes. So we're trying to find the final mass. So So I'm plugging that into this formula here. Okay, so let's simplify this. We know the initial mass is 534 grams. And what's 102 divided by 34? Great. So to do this in a calculator, you go 234 or 534 times 0.5 caret 3. And guess what I got? So I'll put this equation on the board for tomorrow. Okay, that's it. Either a solution is fine. I've already talked to some of you. Some of you like the equation, others like the graphic. We're flexible. To a degree. All right. So, okay, so tomorrow you need to bring calculator. You bring your take-home problem completed. And food. Yeah.
Do we still have this?
Oh, we haven't done that one yet, huh? Yes, that'll definitely.
Yeah. It's in this person.
Okay, so on both of these, I want to know the chemistry. I go in these coughing fits. Guess what brings it on? And when I talk loudly, it's even worse. Okay, so you need a chemistry of coal. Coal is there are 4 kinds of coal. This is the average for all of them. Is it, oh. All right, so it's gonna be 139. Hydrogens, we need 140. And oxygens, we have let's see, how many? Okay, so that's coal burning. And then you always have heat. All right, what's the heat source for a coal-fired plant? Yeah, it can be any of the fossil fuels, but the chemistry is, I use coal. You just say coal's the heat source. Yeah. Okay, what's 1 pro? OTEC. It's cost effective, assuming you have no price put on the environment. What else? It's low cost relative to nuclear, because they're both expensive, but nuclear is far more expensive. Okay, what else?
Inexpensive fuel.
Yeah. Also, it's abundant. Problem is, the high quality coal is not abundant. It's basically used up. The only ones left are the more, the dirtier ones. Okay, what would be a con?
Pollution.
But they have a pond for the ash. But according to our president, we have clean coal. What is this nose? I'm sorry, what? Okay. There's a lot of old ones around, and the old ones are very inefficient. The newer ones, they put in scrubbers in the stack right here. And they take out the ash from the smoke and they deposit it in the pond. Back in the 50s, they had a lot of coal burning plants. And the acid rain got so bad, most of New Hampshire's freshwater lakes are sterile. They got so acidic, nothing can grow in them.
for lecture, you did the other chemical equation, the two C 180. Are you fine with either one?
Yes. Which one did I use?
I screenshotted this, so you did the two C 180H 362.
Oh, I just,
And you said there's a couple of them that.
yeah, the main thing is start with a big carbon.
Yeah,
And then the H's are 2 times the carbons plus 2.
so you're fine. with-
Yeah. Okay, so let's look at the nuclear power plant. Okay, so here's the heat source here. And that's nuclear. And usually it's some kind of fissionable material. You always think of uranium. But there are other things that you can use in there as well. Like the Chinese just built the first thorium nuclear power plant. They beat us to the punch. Okay, so we have uranium 235 plus a neutron. That gives us U-236, which is very, very, very unstable. So it immediately goes to barium plus krypton plus gamma plus lots of heat. So these two need to add up to 92. And krypton is, what, 36? And barium is 56. And what did I leave off? Or something I left off, plus what? 3 what? 3 neutrons. Because those neutrons then start up another reaction. Only it goes from 1 reaction to 3 reactions. 3 reactions to 9 reactions. 9 to 27, 20, you can see how this thing gets big. And that's the reaction that's in a bomb. You want a self-replicating reaction. Now, the problem is nuclear power plants, you don't want a bomb. You want to be able to control it. So we have inside here are control rods. And those control rods go up and down and they absorb neutrons. So that's how they control a reaction. The more the rods go down, the more neutrons are absorbed, and you can't start the reaction without a neutron. So that's how they control it. Now you might add, what if we lose power? You lose power, these are electromagnets up here that are only magnetic with power. So if you lose power, they're not magnetic, so the control rods are up, down, shut off the reaction. Okay. So pros. What's a pro? Yes, cheap power. And it's getting cheaper all the time. They're starting to make micro reactors that they can bring on a site. For example, they have a hurricane, knocks out power all over the place. They can bring in these small reactors and produce lots of power on site. Do a lot of cool stuff with it. Okay. Economical, good. So I'm going to put on no pollutions. Because there's leftover fuel that's radioactive. So that's a con. So radioactive waste products. Now, they store those on site in a pool of water. To make a dirty bomb, you take the leftover from the power plant, you grind it up with a hand grinder, and you go up on a plane and go. That's called a dirty bomb. Every nuclear one, yeah. Mhm. Every single one, and none of them are guarded. They're probably guarded now, but for a long time, they weren't even guarded. Okay, pros, a con is expensive to build. To build and take down. Compared to the coal-fired. Another con is they have to be by water. For the cooling. And every power plant, both coal and nuclear, have these big giant cooling towers. And they're like 4 or 5 stories high. They're really big. And that's how they cool the water after the steam is converted to steam. Okay. So I didn't ask you how it worked. On a lot of tests, when I give this, they have to tell me how this thing works. But all you need to do are these 3 things.